Hi, in this video we are going to study how to represent real numbers in binary. First, let's look at how to represent decimal real numbers. A decimal real number can be defined by this formula. It has three parts: the sign, the mantissa, and the exponent. And we usually use the floating point notation to represent the real numbers. For example, we have these real numbers, and then we can have the corresponding floating point representation. Like this is a real number, and if we use the floating point notation, we can represent this number as this one. Usually, for one real number, we can have multiple floating point notations. For example, here we have 3.14159. And this number can be represented using the following different floating point notations, and all of them means the same value. The only difference is that we change the position of the vertex point, and at the same time we change the exponent. For example, this number means that we can represent the vertex point one position to the right, because the exponent part is 10. And for this number, we have to move the vertex point 2 positions to the right, because the exponent part is 10 to the second power. So if we move the vertex point 2 positions to the right, it will be 1 and 2, 3.14159 equals to the first one. So the floating point notation has three different parts: the mantissa part, the base, and the exponent. The mantissa part means the number itself, the digits, and the exponent means the position we want to move of the vertex point. A numeric float format that can be used to represent very large real numbers and very small real numbers is called the floating point notation. So the floating point numbers are stored in two parts: the mantissa part and the exponent part. The mantissa part means the numerical value, and the exponent part means the real position of the vertex point. So we have two parts, exponent and mantissa. So for each of the part, we also have one sign bit. So for the mantissa part, we have the sign bit to represent whether this number is a positive number or negative number. For the exponent part, we also have a sign bit. The sign means we're going to move the vertex point to the left or to the right. And the digits in the exponent part means how many positions we're going to move. Because we're going to represent the number in binary, so we don't need to represent the base, because the base by default is 2 in binary. So we have this number in decimal. First of all, we can convert it into binary, and this will be the binary representation of this number. And then we can change this one into a floating point notation. So if we move the vertex point one position to the left, the number will be changed to 0.11011, because we want to keep the value same. So we have to multiply the power to move the vertex point one position to the right to keep the value unchanged. Or we can use this representation. If we move the vertex point 2 positions to the left, and then we multiply this power, it means we're going to move the vertex point back to its original position. Or we can use this representation. So these are the three representations of the three floating point number. For the first one, the exponent part is positive 1. So the sign of the exponent is 0, meaning the positive, and the value is 1. For the second number, because the exponent is positive 2, so this will be positive 2. And for the third one, because the exponent is positive 3, so the exponent is positive 3. For the mantissa part, because all of the three representations are positive, so the sign bit of the three representations are all 0. And by default, the radix point is located here right after the sign bit. So the mantissa part for the first number is 11011, and then fill a lot of zeros. For the second number, the representation is 0.011011, and then zeros. For the third number is 0.00111011, and then a lot of zeros. So these three representations represent the three floating point numbers. So in this case, for one number, we can have different representations, so which is not convenient for the computer to have a standardized way to represent the number and to calculate the value of the number. So we are going to normalize the number so that we can have a standard representation for each of the floating point number. So the normalize means that the first bit of the mantissa part must be 1 to prevent multiple representations of the same value. For example, we have this number, which is a decimal. If we want to normalize this number, we are going to get this one. So after the radix point, the first number must be a non-zero. So this number can be changed to 0.123. But the original number is 0.000123, so it means we are going to move the radix point 1, 2, 3 positions to the right. So in order to keep the value unchanged, we are going to multiply this power, and it means that we are going to move the radix point 3 positions to the left to keep the value unchanged. It is same in binary. So if we have this number in binary, and then we're going to normalize the value. So because we have to make the first bit after the radix point be 0. So we are going to move this radix point from the current position to 1, 2, and 3 positions to the right. So the mantissa part will be 0.101, and the exponent part will be -3 because we are going to move the radix point back. So we have to move 3 positions to the left to keep the value equals to the original one. So if we have 12.345 in decimal, how are we going to represent this number in computer? So let's look at this example to represent this decimal number in binary. So the number is 1.6875. And we are going to use 32 bits to represent this number. And for the 32 bits floating point notation, we are going to use 8 bits for the exponent part and 24 bits for the mantissa part. So first of all, we are going to change this number into binary. So 1.6875 will be 1.1011 in binary. And then we're going to normalize the value. So we have to move the radix point 1 position to the left. So the normalized representation of this number will be this floating point notation. And then we are going to use 32 bits to represent this number. First, let's look at the exponent part, which is +1. So it's quite easy to represent +1. So this will be the exponent part. For the mantissa part, is a positive number, so we keep the sign bit 0, and then we have 0.11011, and then we are going to fill all the other positions with zeros. So this will be the binary representation of this floating point representation. Let's look at how to represent a negative number in binary. So we have -1.6875. So we still use the 32 bits floating point notation to represent this number. So first of all, we change this one to binary because it's a negative number. So the binary number will be -1.1011. So we're going to normalize this number into this form. So the number is still a negative number, and then we move the radix point 1 position to the left. So in order to keep this value unchanged, we have to multiply this exponent, meaning that we are going to move the radix point one position to the right. So now let's represent this number. So let's first look at the exponent part. It's still positive 1. So this is the exponent part. For the mantissa part, it's a negative number, so the sign bit will be 1. And the number is 0.11011. And then we are going to fill all the positions with zeros. So this will be the representation of this number. With the floating point representation, we can represent very large or very small numbers. For example, in a 32-bit computer, if we use 8 bits for the exponent part and 24 bits for the mantissa part, the range will be this one. So we can represent very large positive integers or very small negative integers. We can also represent very small fractional numbers, very close to 0. Let's see which is the largest number. So we have two parts, the exponent part and the mantissa part. So the largest number must be a positive number. So for the mantissa part, the sign bit must be 0 to represent this number is a positive number. So to make it very large, so we can put all the fields with ones. Okay. So we totally have 23 ones. So for the exponent part, in order to make the number very large, we are going to move the radix point to the right. So the sign bit of the exponent part is also 0. And we're also going to put all ones for all of the positions. So we totally have 7 ones here. So this will be the largest number. For the exponent part, the value for this one is 2 to the 7th power minus 1. Okay, so this is an exponent. And for the mantissa part, it's a little bit complicated because the mantissa part is a fractional number and the radix point is just after the sign bit is at here. So this value is actually 0.11111. So what is the value for this one? It's not very easy to know the exact value, so let's do it in another way. So suppose we add this number with another number, which is 0.0000 and then 1. So the sum of these two numbers will be 1 because 1 plus 1 equals to 10, and then we have 10. We carry here. So the sum of these two values is 1. So this value is 1 minus 0.0001. So there will be totally 23 bits. So this number is 2 to the negative 23rd power. So the value is 1 minus this one. So this will be the mantissa part. So the largest number will be 1 minus 23rd power times, this is the base, so the largest number will be this one, which is approximately equals to this number. The smallest number will be a negative number. So the only difference between this number and the smallest number is that we can just change the sign bit of the mantissa part to make it a very small number. So we can change the 0 to 1. So this will be the smallest number, okay, which is negative this number. So what will be the smallest absolute value? So how do we get this one? Let's try to represent this number. We still have the exponent part and the mantissa part. To make the number as small as possible, we are going to make the mantissa part as small as possible. Except the sign bit, we have to put 1 at this position because this is a normalized representation. For the rest of the positions, we can put zeros, because to make it small, right? And for the sign bit, we can put it positive or negative because if we get the absolute value, the sign bit doesn't matter. Now let's look at the exponent part. First of all, let's decide the sign bit. Because we want to make this number as small as possible, how to make this number smaller? So because currently this number is 0.1, if we want to make this number smaller, we have to move the radix point to the left. And for the rest of the bits in the exponent part, we have to make it large because this part is the integer number. It means how many positions we're going to move the radix point to the left. So this part will be ones. So this representation means the smallest absolute number. For the mantissa part, it's easy. It's a positive number, so the number is only 2 to the negative 1's power, right? And for the exponent part, it's a negative number. And the value for this one is, and the value for this part is this value, right? So this is the exponent part, and this is the mantissa part. So the value for this one is mantissa part multiply, this is the base. So the value is 2 to the negative 128 power. So if we are not using the normalized format, so we are going to change this one from this position to the very right. Okay, so this number will be 2 to the negative 23rd power. And for the exponent part is still this number, which is 2 to the negative 150 power. So this number is the absolute minimum number except 0. So in this case, we can show you that if we're using the floating point representation, we can represent a very large range of the numbers. Use binary to represent logical data is easy because similarly as binary, logical data also has 2 states. So it has true and false. So we can easily represent true and false using binary. So in this case, we use 1 to represent true and 0 to represent false. So we can use binary to represent the logical value in these conditional branches. We have 3 types of logical operations: AND, OR, and NOT. For AND operation, the result is true if both of the inputs are true. Otherwise, the result is false. For OR operation, the result is true if either of the input is true. Otherwise, the result is false. meaning if both of the inputs are false, the result will be false for R operation. For NOT operation, it only takes one operand, meaning if the input is true, the output is false. If the input is false, the output will be true. For the AND operation, it's just like a series circuit. You have two switches in the circuit. You have to close both of the switches to turn on the LED. This is the truth table of this operation. So A and B are two inputs, C is the result. So only this can generate a true because both of the inputs are true. R operation is just like you have two keys for the same lock. You can use either of the key to open the lock. So this is the truth table of this operation. And only both of the inputs are false, the result will be false. Otherwise, the output will be true. This is NOT operation. So it will just reverse the input.